So we're going to continue our discussion on enthalpy, and in part 2 we're going to continue the thermochemical equations, and then we are going to tie it to stoichiometry. So we learn about thermochemical equation, we know what those are, and we've done stoichiometry, so let's bond these two together. Okay, but before we start, let's have a revisit on the first law of thermodynamics. So you see the top equations here, that might not be familiar to you, but if you remember the first law of thermodynamics, what did we say? We said the change in enthalpy in internal energy is from Q and W, right? So it says at constant pressure, right? So what is heat in constant pressure? We just learned about this in the previous video, enthalpy, right? So Q in constant pressure is delta H, right? And if we are dealing with gas, we learned about how to calculate work, right? And work is negative P delta V, right? So if I rewrite Q plus W in constant pressure, then we would have the same equation we have on the top. The delta E is delta H, which is Q, plus W, and we have a negative sign, so it's negative P delta V, and that's the same equation we have in the top. Okay, so as constant pressure, the first law of thermodynamics says that at constant pressure, internal change in internal energy equal to the change in enthalpy minus P delta V. So if in a course of a reaction there is no change in the number of gas moles, so if you remember, if we are making more gas, we have expansion. If we are making less gas, we have compression, right? And that expansion or compression is going to do the work because we have delta V, right? So if in a course of a reaction we don't have a change, we have no change in the number of gas moles, what happens? Then there is no compression or expansion, and the delta V, so let me rewrite this equation first. So delta E equal delta H minus P delta V. So if the number of moles is 0, then the change of volume is 0. So this whole term is 0. Therefore, delta E equal delta H. And that's true for most of the reactions. Okay, for lots of reactions, you would see that we might say the change in energy, but we have delta H. As you might have heard me in the previous video, I say that the amount of energy, which was basically the amount of enthalpy, but you can use these terms interchangeably sometimes because it's almost the same. And why is it like that? It's because even though there is a change in the number of gas moles, the amount of change from this term, the P delta V term, is so small that even though if we write it as delta H plus P delta V, the P delta V term is so small that delta E is almost equal to the delta H. It might be a little bit different because we're adding this P delta V, but still the change is not that much. So the amount of change in the internal energy is almost the same as the change in enthalpy. So if you think about the gas law, that's one of the most famous equation in the gas, ideal gas, PV equal nRT. That's a very famous equation. So if we take that and we try to substitute the P delta V, we can get RT delta N. Okay, if the temperature is constant and pressure is constant, we have only the change in volume and change in number of moles of gas make this change in the volume, right? So if I substitute the P delta V with this equation, I would have RT delta N. Okay, and this N is the number of gas moles. Okay, so I would get delta E equal delta H minus RT delta N. So let's practice this on this example. So we want to calculate the change in internal energy, delta E, when 1 mole of CH4 reacts with 2 moles of oxygen at 298 Kelvin temperature according to the following reaction. So we have this reaction, and in this reaction you see that all of these phases are gas, and we have a delta H. Okay, so we want to try to find delta E. We learned that delta E is delta H, and these are gas, delta H minus P delta V, or we can say RT delta N. Okay, and delta N is the change in the number of gas moles. So just like all the delta that we defined is final state minus initial state, so which is product minus reactant, right? So delta N, how many gas moles do we have in the reactants in the product side? So we have 3. We have 1 mole of CO2 and 2 moles of water, so we have 3 moles in the product side. How many gas moles do we have in the reactant side? We have 3, 1 CH4 and 2 O2, so we have 3. So therefore delta N is 0, so this whole term equal to 0. So delta E equal delta H, and that is equal negative 890.4 kilojoule. Okay, but let's assume, so let me draw a line here. So for this question, that would be the answer, and delta E would be negative 890.4 kilojoule, right? So, but let's assume that we have liquid water, okay, not gas phase, not steam. So in that case, what is the delta E? So we have to find the delta N again. So how many moles do we have? How many moles of gas do we have in the product side? Well, this is now liquid. We only have CO2, so there's only 1, minus the initial state, the reactants. How many gas moles do we have in the reactant? We have 3. So now delta N is negative 2, right? So to find the delta E, it's delta H minus RT delta N. Okay, so I write it here. Delta H is negative 890.4 kilojoule minus R. For R, we have different values for R. You have to find the right number, and you have to check the unit. So if you check 8.314 value for R, have the unit of joule over mole Kelvin. Okay, so this is still joule, but my enthalpy is kilojoule, so I have to convert that to kilojoule. So I don't want joule, I want kilojoule, and 1 kilojoule is 1 to the 3rd joule, 1000 joule. Okay, times so that my RT is given in the question is 298 Kelvin, and delta N is negative 2 mole. Okay, so you can see that these terms cancel out, mole with mole, Kelvin with Kelvin, joule with joule, and we end up with kilojoule, and we have kilojoule here, so we can do the subtraction, right? So this whole term is negative 4.96 kilojoule, and we have negative here and negative here, so that would be addition. And so we have addition here and we have negative sign, so the answer is negative 885.4 kilojoules. So you see that even though if we have a change in the number of gas moles, the amount of delta H is 890 kilojoule, and the whole amount for the term of P delta V is just 4.96, so it's not that much. So even though we have a change of number of gas moles, the amount of internal energy, the change in internal energy is almost the same as the change in enthalpy. Okay, so let's continue to examine the equation. So we have this equation and we have the enthalpy. So we said that the coefficient represent the number of moles, right? So when we have 1 mole of when 1 mole of CO2 is produced, what is the enthalpy change? So the coefficient for CO2 is 1. Therefore, for 1 mole of CO2, we have the same amount of delta H, right? So this amount of energy, this amount of enthalpy, you see, we use it interchangeably, energy or enthalpy. The enthalpy change is negative 890.4 kilojoule. So now you answer this. If two mole of oxygen is used up, what is the change in enthalpy? Yes, because the coefficient of oxygen is 2, so for 2 moles of O2, we have the same change in enthalpy, and that's negative 890.4 kilojoule. Okay, so if when we have 2 mole of oxygen is reacted with excess of CH4, what is the enthalpy change? So how do we do that? So in the coefficient in a balanced chemical equation, we have 2 moles of oxygen with this amount of energy. What about 2.5? How do we solve these kind of questions? We've learned about stoichiometry, right? And we know about thermochemical reaction now. So let's go to the next slide and see how we can solve these kind of questions. So just like what we did in the stoichiometry, we can use the concept in the thermochemical equation as a conversion factor, as a unit factor, okay? So in the usual chemical equation, we use stoichiometry and we use the coefficient, the balanced chemical equation. I would say, for example, 2 mole of oxygen is 1 mole of CO2, right? They were equal and you could use them as a conversion factor. Now, with a thermochemical equation, we can use the amount of delta H with the coefficient of the balanced chemical equation and use that as a conversion factor. So we start, if you have this question like the one we had in the previous slide. So if you have 2.5 mole of O2, how much change in enthalpy? So we know that for 2 moles of O2, we have this change in enthalpy, right? So I can use that as a conversion factor. So I don't want the moles of O2, I want the kilojoule as a change of enthalpy. And these two cancel out, and we end up with the amount of change in enthalpy, the delta H, okay? So that's how we use it. We can use the delta H and the coefficient in the balanced chemical equation, or let's say thermochemical equation, and we can use that as a conversion factor. So that is a new tool in our conversion tools, right? And this tool is the conversion between mole and kilojoule, okay? So when you want to go from mole to the change of enthalpy to the kilojoule, you can use this conversion tool. So let's have a practice on what we've learned. So determine the amount of heat in kilojoule given off when 1.6 times 10 to 4 gram of ammonia are produced according to the reaction below. Okay, so you should be mastering this right now. So we've done this a lot of time. We've learned dimensional analysis, we've learned stoichiometry, so we should be able to do that. So we start with the mass of, we start with given information, right? The information we have is the mass of ammonia. So let's start with the mass of ammonia. So the mass of ammonia is 1.26 times 10 to 4 gram. So what you've learned in stoichiometry was that when we have mass, we always have to go to the mole to use the mole bridge. and in this case we want the amount of heat. So from mole we can go to the enthalpy, the amount of heat, right? So from mass I need the molar mass of the ammonia, which is 17.031 gram of ammonia, NH3, and that's NH3 is 1 mole of NH3. So I want to find the amount of heat. So we have 2 as the coefficient, so 2 moles of NH3 have the heat exchange of negative 92.6 kilojoule, right? So gram of ammonia with a gram of ammonia, mole of the ammonia with a mole of ammonia, and we end up with a kilojoule. So you just put these numbers in the calculator and come up with a number, and that equal to negative 3.42 times 10 to 4 kilojoule. So therefore the answer is C. Okay, so where we are going next is to finding the amount of change in enthalpy, the delta H, and there are 4 different ways to find that. So since now you've learned about thermochemical equation and delta H is given in the equation, but we're going to learn some methods to find delta H. And the first one is the calorimetry, and which is the experimental way of determining the delta H, and that's the most challenging part. So we're going to talk more about this in the next videos. And the next is Hess's law, and the third one is using the heat of formation, and we are going to cover these 3 in this chapter. And the last one is not for this course, and that's for way ahead in the next courses, that we're going to estimate it using the bond dissociation energy. So for this video we continue to learn about thermochemical equations, and we've learned about that the delta H and delta E is almost the same, have the same value, and we've learned how to merge the stoichiometry concept with our thermochemical equations, and how to use them in our dimensional analysis, and use the delta H with the coefficient as the number of moles as a conversion tool in our dimensional analysis.